So thanks everyone for coming here instead of going out to eat more free food. I'd like to thank the organizers for giving me this opportunity. So I'm a student of Robin Graham's at the University of Washington, and this is work is joint with him. This is actually sort of a continuation, a sequel to his talk. So for that reason, this will be not self-contained, but what it lacks in self-containment, it should also lack in redundancy. So first, let me say just a little bit more about tractors. Mostly here I'll be talking about the parallel tractor extension theorem that Robin was discussing. He mentioned tractors briefly. I'm going to say a little bit more about that, not too much more, so that I can make a more precise framing of the main theorem. So always in this talk, we're going to have a fixed conformal manifold, a manifold M with a conformal structure C of potentially mixed signature, and we can always associate to that a metric bundle, and we can also associate, we can pick a choice of ambient manifold, and that ambient manifold is determined up to some ambiguity depending on the parity of the dimension. So tractors are, this is not a standard definition of tractor, but this is the definition of tractor that makes this talk the shortest. So tractors are going to be sections of, they're going to be vector fields or restrictions of vector fields on the ambient manifold, restricted to the metric cone or the initial surface, sometimes we call it, with the proper homogeneity with respect to dilations that maps Robin called delta S in his talk. And so we're going to denote the bundle whose sections are tractors, that is the tractor bundle, by this script T. So for someone who is asking about what tractors are in a previous talk, this is an alternate definition for that. All right, so just like we can with any vector bundle, we can form the dual, and we can form tensor bundles of various types. All right, so in particular, there's the Levi-Civita connection on the tangent bundle to the ambient space is going to descend to a connection on the bundle. In fact, the homogeneity is selected so that this works in the way that we want it to. And a consequence of this is that if we have a parallel tensor on the ambient bundle, that is a tensor so that its covariant derivative is equal to 0. The descent of that applied to the restriction is also going to be 0. In other words, if we restrict a parallel tensor, then we're going to get a parallel. If we're going to restrict a parallel ambient tensor, we're going to get a parallel tractor tensor. All right, and both of these objects are of interest. They occur naturally in various settings. Parallel tensors, at least from my point of view, are most interesting because they're associated with special Holonomy types. Robin said a little bit of that, and I'll be able to say a little bit more about that too, depending on time constraints. And parallel tractor tensors have various uses. You can actually define the tractor connection in terms of Einstein scales, and this conformal Einstein operator was. Oh, so an Einstein scale is just a scale that gives you, it's basically a specification of an Einstein metric inside a conformal class. So in other words, if you have a conformal structure that's conformally Einstein, the Einstein scale is basically a way of specifying, right? And you can probably, if that's was your question, you can probably safely ignore the word almost here, at least temporarily. Also, the classical Pfefferman conformal construction, if you form a tensor bundle associated with that conformal structure, then that tensor bundle is always going to have, that tractor bundle, or rather the tractor two-form bundle is always going to admit a parallel section in that case. So if you don't know these terms here, the important thing is just that we do have interesting examples of places where these already occur in the wild. So there's a natural question here. When can we reverse this restriction? That is, when can we start out with a parallel tractor and produce a parallel tensor on the ambient manifold? And so the original motivation for this, actually the original question of this project, was not about tractor extension in this generality, but it was this very specific case. We were interested in somehow producing groups of holonomy contained in and eventually equal to the split real form of G2. And I won't say too much more about this, but just to remind you, our method for doing this was to extend a parallel tractor into the ambient direction. So here's our main theorem again. Again, Robin presented this, but because this is the sort of centerpiece of this talk, I'll state this one more time. So here, chi is any tractor tensor of any type of symmetries. So suppose we have a parallel tractor tensor, then the parallel tractor extension theorem says that we're always guaranteed that there's some extension that is parallel up to some order. And that order, again, depends on parity. This is another example of what Mike mentioned earlier this morning when he said that conformal geometry is very different in odd and even dimensions. So again, Rod Gover showed this in the R=1 case, and it turns out that this is actually almost trivial in the Einstein case. That is, when your conformal class is conformally Einstein. In that case, we can actually just write down an explicit formula. The ambient metric case, in that case, decomposes as the sum of a cone metric and a line. So it's also worth pointing out that if C is real analytic, then, for example, in the case when n is equal to odd, or excuse me, in the case when n is equal to odd, then of course something that vanishes to infinite order actually vanishes if it's real analytic. And the important point here is that we really do get a bona fide parallel extension. That's really what we needed to guarantee G2 holonomy. So R is, again, this is one of those disadvantages of not having a blackboard. Right, it's just code for the rank of the tensor. And again, Gover's method here was actually very different from ours. All right, so leaving the real analytic case, passing back to the general case again, just like in the ambient metric, the even case in the even case, parallel tractor extension is much more pathologically behaved than the odd dimensional case. For the most part, we've really only considered C with, or that is conformal classes that are obstruction flat. There's an obstruction associated to any conformal class that tells you whether an ambient metric can be written down in the even case that's Ricci flat to infinite order. Generically, it's only flat to order something like n/2. All right. So in the case when a conformal structure is obstruction flat, however, we actually get infinitely many different ambient metrics that are all vanish, or whose Ricci curvatures all vanish to infinite order. All right, so there's a natural question. Given any parallel tractor on an even dimensional manifold, and again, we're going to restrict our attention to the obstruction flat case, it's conceivable that we have different ambient extensions for different choices of ambient metrics. And so we can ask for how many is this true. And it turns out that there are lots of different possibilities that depend on the case. Sometimes there are none. I won't say too much about this, although it's a really interesting example. If you know what a Poincare-Einstein metric is, then the almost Einstein scale to that, which you can view via a BGG splitting operator as a section of the tractor bundle, is going to admit a parallel extension if and only if that Poincare-Einstein metric is actually what we call even. I also don't want to say too much about this example because it's also fairly technical, but you can actually get infinitely many extensions, or that is, there are infinitely many choices of ambient metric in this case that admit a parallel structure. And in this case, this is just the Pfefferman conformal structure that I was talking about before. And again, a Pfefferman conformal structure always admits a parallel tractor 2 form. And I should also say that only applies to the case when we're talking about a hypersurface of CN, a non-degenerate hypersurface of CN. So to try to tame this as much as possible, we've come up with this condition called determining, which is a simple algebraic condition on chi that's given in terms of the natural SO p plus 1 q plus 1 action on tractors. And if I won't tell you what this question or this condition is, this determining condition is, unless someone asks about it later. But it's a very easy condition to check, or at least it's a very simple condition to write down. And so one can show that a non-zero tractor a non-zero parallel tractor admits at most one extension admits an extension for most one choice of ambient metric if that parallel tensor is what we call determining. And there are lots of different cases, lots of different special cases in which a parallel tractor tensor is determining, and here are a couple of examples. If our parallel tractor is symmetric and trace-free, then it's automatically determining. Likewise, if we're in the case where C is actually definite signature, C is signature N0, and our parallel tractor is actually a parallel form, then we're also going to have at most one extension. So I'd like to say just a little bit about the proof. This is my last slide. So first of all, we started in sort of the most naive possible way. We already know that we can view, in fact, in this lecture by definition, we can view tractors as sections of the ambient tensor bundle restricted to the initial surface, that is restricted to the metric cone. And so if there is an ambient extension, then in particular it has to be ambient in the rho direction. Here, rho is just a coordinate that's transverse to the metric cone. So here, the first thing that we do is we just parallel translate our parallel tractor in the rho direction. And again, if we're going to have if this extension, if this candidate extension really is going to be parallel, it has to, in particular, be parallel along these lines. All right, so once we have that candidate, then it turns out that it's enough just to check that all the covariant derivatives vanish along the initial surface. And we can analyze the individual components of the covariant derivatives of this candidate extension one at a time, and also inducting on the number of derivatives k. And it turns out that most of these are actually fairly easy to handle. The one of these that's difficult is basically analyzing this one here, where the first derivative index is tangent to the base manifold M, and the other indices are all in the transverse direction. And this requires some ambient curvature identities that I won't specify here. So it turns out this induction step works unless k is equal to 1/2 times n minus 1, and this is exactly why this induction carries through to infinity in the odd dimensional case, and why we have this obstruction that's analogous to the ambient metric obstruction at precisely this order. All right, so let me just say one more fact about this. This theorem can also be framed in terms of integrability conditions for parallel tractors. So if we have if there is an infinite order ambient extension of one of our tractors, then in particular for all k, this identity here is going to be true. And here, this is just the standard p plus 1 q plus action, or q plus 1 action. And so in particular, we can regard this condition right here as a condition on tractors. And letting k vary, we can, and also choosing different combinations of indices, we can come up with some large list of a large list of integrability conditions for parallel tractor tensors. Okay. All right. Well, thank you very much. Yeah, yeah, two different parallel attractors.
Ambient metrics that you really have two parallel attractors.
Yes, I mean that should be true. I mean, I think there are. Robin can probably say a little bit more about this. I mean, I think that the case where there are where there are distinct Einstein scales, that is, Einstein scales that aren't just constant scalar multiples of each other, those cases are completely classified, if I remember that correctly. But there's nothing wrong with having two distinct parallel attractors.
So if you have each parallel attractor, it's a separate question. Does that parallel attractor have a parallel extension for the ambient metric? So each one of them will. So in the conformal Einstein case, all parallel attractors have a parallel ambient extension. So if you have two, I mean, you have the same conformal class. You have one ambient metric for that conformal class, and there's two parallel attractors because you have two Einstein scales. Each one of those will have a parallel ambient extension.
The question is, can this happen in this G2 frame that you have, you have your metrics from your talk, and you find a conformal scale which preserves this G2 split G2?
So is the question, can these G2 metrics, or can the attractors that give us these G2 metrics also admit an Einstein scale?
No, I think he's saying can a given Mirovsky conformal structure have two different parallel attractor freeforms? I think that sounds like what you're asking.
Oh.
Let's see. So I think probably the Hamelin-Sagerschnick theorem is relevant there because it says that it characterizes the conformal structures in terms of the existence of a parallel attractor freeform. So I would think that means that you can recover the conformal structure from the parallel attractor freeform. So you can only have one.
It sounds like it would force the whole and maybe be smaller than G2.
Yeah, if you've got any conformally Einstein, you're certainly going to. I mean, that's a different question. I mean, it would certainly mean your polynomial is going to drop. But I don't think we could see. But I think maybe the Hamelin-Sagerschnick theorem would say that can happen.
In that particular case, when you do have one of these metrics G and there is an Einstein scale, the ambient metric in that case is actually going to be contained inside the parabolic P that Robin mentioned in the last talk, the nine-dimensional stabilizer of a null line in the model case.